In lecture 6, we're going to continue talking about MLEs. And we're going to start off by just doing a bunch of examples. This is going to be particularly helpful for homework tests where we'll have examples. The nice thing about MLE problems is that they're kind of relatively simple calculus problems, and so they're easy to write homework and test questions about. So let's just do some examples for a little bit here. So my first example, let me back up actually. Let's do a real quick recap. Since it's been a weekend or so, right? So MLEs, we define a likelihood function, L of theta. It's basically a rebranding of the joint PDF, F theta of x, but we're viewing it instead of as a function of the x's, as a function of theta. We also work with the so-called log likelihood function, which is the natural log of the likelihood function. And the idea behind MLEs is that if I look at, say, L of theta, and I look at this thing as a function of theta, this is going to have some graph we could draw. And it basically, each point here, each point describes, what we're thinking of is that the data, the x's are fixed for a fixed set of observed data points. So we're thinking of this as the x's are fixed. The, quote, likelihood, which is the density or the probability of observing these x's given that my true parameter is some value. So maybe at this point corresponds to some value theta not. So the point here on my red line would be basically the likelihood of, given I've observed my x's, it's the likelihood of observing the x's if my parameter theta were theta naught. And so I could try this out for each of my different values of theta, and a reasonable principle, it would seem, is that the value of theta that I should estimate, which we call theta hat MLE, should be the value that maximizes my likelihood. And so basically all I'm saying is I'm going to guess. I don't know what theta is. It's unknown. I've observed some data, and this data should tell me something about this unknown parameter theta. And what I'm going to guess, and the fancy word for guess we use is estimate. I'm going to estimate that theta is going to be the value that is most likely to have occurred given that my data is what it is. Given my data is what it is, I'm going to estimate theta to be the value of theta that is most likely given that data. And so MLE problems basically boil down to forming the likelihood function and then finding the value theta hat that maximizes that likelihood function. So these often are kind of calculus problems because maximizing a function is kind of a Calc 1 problem. Not always. We don't always have completely differentiable functions. So sometimes we get to do something a little fancier, and we'll talk about that today. Anyways, let's do some examples. So here, maybe I assume that I have some data, and it's going to come from a Poisson distribution. And this Poisson distribution has some unknown parameter theta, lambda. So things that are Poissons are counts. The support for a Poisson is 0, 1, 2, 3, 4, etc. So, something like, how many fish do I observe in a river in a certain time period? That might have a Poisson distribution. It's a count. I have 0 fish in a certain time, 1 fish, 2 fish. And I want to estimate this parameter lambda, which is basically the average number of fish I would expect to have in this river in a certain amount of time. Right? So there's a practical example of why I would want to estimate lambda. Fish is a good example. Poisson is French for fish, right? But there's other examples. So radioactive decay is a Poisson process. There's a Poisson distributed. Let me be careful there. Has a Poisson distribution. So maybe I measure how many radioactive particles I get in a certain time period, and I'm interested in the average number I get in the time period. So I want to estimate the parameter theta, or parameter lambda here. Okay. How do I estimate it? Well, we could do this with method of moments. We might have done this. We can also use the maximum likelihood estimator. And so the maximum likelihood estimator is going to say, first, let's form a likelihood. And my likelihood is just basically write out my joint distribution. And as we said in the first lecture, the joint of a bunch of independent data is just the product of the marginal. Each of these are marginally Poisson, and the Poisson distribution has, for some parameter lambda, has the form. What is the form? It's e to the negative lambda times lambda to the x sub n over x sub n factorial. It's a Poisson distribution. And we can play our fun tricks. I can push through this product, right? Because it's the product over all the possible x sub n's. This would be e to the negative n lambda. I'm going to start skipping over some of these basic algebraic manipulations. This e to the negative n lambda. Lambda to the sum, the x sub n's. And if you need to pause it and work out why that's true, you can work out why it's true. I'm going to just assert that these facts are true. And then I can have this thing in the basement here, which is going to be the product of my xn factorials. Not super nice, but that's what it is. And so this is a likelihood function. And we've said that Poisson is an exponential family, and so you might find it useful to work with, instead of the likelihood function, the log likelihood function. So little l of lambda is the log likelihood function, which is literally just the log of this thing. In this case, when I do that, it will be negative n lambda log of e is 1. Cool. Plus, because I have a product, so whenever you see a product, turn that into a plus in the logs. I can pull down this sum. So I have sum of the x sub n's times log of lambda. And then I get minus, because whenever you see a division, you can put a minus when transferring from normal scale to a log scale. And I could say it's the log of the products, or I could say it's the sum of the log of the factorials. Is what it is. That's the log likelihood function, and we want to maximize this thing. So this is kind of step 1, write the likelihood, or log likelihood. Step 2 is maximize this. Look at dl d lambda. Take a derivative of little l with respect to lambda. Negative n lambda just becomes negative n. And then derivative of log lambda is 1 over lambda. So I still have my sum up top. And this last term actually doesn't involve lambda at all, so that goes away. If I set this equal to 0, then I'm going to solve back for lambda. Call that lambda hat. So basically I'm solving this for lambda. What do I do? I move the n over, I multiply by lambda, I move the n back over, something like that. And what I would find is that lambda, or indeed our MLE lambda hat, is going to be x bar. That's the MLE for Poisson distribution. Turns out it's just x bar, which is nice because it didn't have to be that way. We'll see examples where it's not always that way. nicely enough here. Poisson, the mean parameter, lambda we're estimating, is just estimated nicely by the mean of the data. So that's cool. Let's keep looking at some more examples here. Let's look at maybe an exponential distribution. Assume that we have data that comes from, that is exponentially distributed. This also has a parameter lambda. Lambda is not the mean here. It's actually the reciprocal of the mean. So recall that the expected value of any by exponents is 1 over lambda. So this is my exponential distribution has a PDF of lambda e to the negative lambda x. This is for x positive. So how do I solve this problem? Step 1, form the likelihood function, which is the product of the marginals. So now I'm just being real quick and real lazy. And in that case, what are my marginals? Lambda e to the negative lambda xn. You could write this indicator in here. Basically, because it doesn't depend on theta, it's not actually going to matter. Let's just do it to show it. But you're going to see that this thing disappears when we take a derivative because it doesn't depend on lambda. Note for the next example, if that indicator does depend on lambda, we're going to be in a problem because that indicator function is not differentiable as a jump discontinuity, right? Basically at 0 in this case. So in this case, it would be lambda to the n, e to the negative lambda times the sum of the x sub n's. And then I'm not really, well, let's just write it this way. I guess this should be x sub n here, shouldn't it? So it's indicated that the x sub n's are positive. Now, again, this is pretty unnecessary for this problem. If all of the x, so this is saying that x1 is bigger than 0, whenever I, again, if you recall, whenever I multiply two indicators of a and b, this is the same thing as the indicator of a and b. So indicator a times indicator b is indicator a and b. If I take like the product of these indicators, this would say that x1 is bigger than 0, and x2 is bigger than 0, and x3 is bigger than 0, and etc., etc. So we could rewrite this whole thing. The product that all of the x sub n's are bigger than 0, you could rewrite as the product, as the indicator that the minimum is bigger than 0. Because certainly if the minimum is bigger than 0, they're all bigger than 0, and if they're all bigger than 0, the minimum is bigger than 0. So that's if and only if. So you could rewrite this thing as lambda to the n e to the negative lambda sum of the x sub n's, indicator that the minimum, let's write it like this, the minimum is bigger than 0. That trick will come in handy more so in the next one. If you take the log of this, right, and this is n lambda minus lambda, we play our tricks with our logs. Right, so we get this log as the indicator, which is very weird, but not to worry. When we come to step 2 here, we look at dl d lambda. What do we get? We just get an n minus whoops, we don't get that lambda, minus sum. That whole log of indicator goes away, so I really didn't need to worry about that too much in this problem. It doesn't depend on lambda. So when the indicator comes from the support of the distribution, when the support of the distribution doesn't depend on lambda, doesn't depend on the unknown parameter, we don't really need to pay too close attention to it. That will be true of any exponential family. We've basically defined exponential families so that you cannot have the support of the family of the distribution depend on the unknown parameter. And so in this case, it's pretty simple. What we get when you look at d lambda, it's n minus, and oh, we're missing a lambda here. What happened? Did something wrong. This should not be lambda, it should be log lambda, right? So this is n over lambda. I'm going to take a derivative. Now we have a lambda, which we can set. And so in our equation, we set this equal to 0. We find that lambda is going to be 1 over x bar. And so we'll call lambda hat our MLE, which is 1 over x bar. So that's kind of interesting. If you recall, the expected value of any of these is 1 over lambda. So certainly the expected value of x bar is 1 over lambda, right? That goes back to first lecture, where we said x bar doesn't change the expected value. So the expected value of the x events are 1 over lambda. The expected value of x bar would be 1 over lambda. So this makes sense. If I want to estimate lambda, basically I'm solving back. So this is, right, this would be a method of moments estimator also. And this makes sense because, so lambda hat, the estimate of the parameter lambda, is 1 over x bar. It doesn't have to work that way, but it does in this case. The follow-up is that if I had data that followed some distribution parameterized by a parameter beta, so there's another way of parameterizing the exponential family, which is in terms of parameter beta, where it's 1 over beta e to the negative x over beta for x bigger than 0, right? So if you look, this is exactly the same form as this, except I've replaced the lambda for 1 over beta. So lambda is equal to 1 over beta. And one could ask, if I gave you this problem, what is the MLE for beta? If you know that the MLE for lambda is 1 over x bar, and we know that beta is just 1 over lambda, or lambda is 1 over beta, by the transformation property of MLEs, since beta is 1 over lambda, then the MLE, beta hat MLE, this is lambda hat MLE, is equal to 1 over lambda hat MLE, which is 1 over x bar, it's x bar. So in our case, for the rate parameterization in terms of lambda, the MLE is 1 over x bar. If I parameterize in terms of this beta, it will give me the MLE is x bar. Notice that here in this parameterization, the expected value of my x sub n's is beta. So that makes sense, or 1 over lambda, right? Beta 1 over lambda. And so if I want to estimate the mean of these, I estimate as x bar. If I want to estimate 1 over the mean, that is I want to estimate lambda, it's 1 over x bar. So that makes, saves us having to do it twice. And that transformation property of MLEs is super nice. Because I could ask for any kind, it doesn't have to be function 1 over, it could be any kind of complicated function of the MLE that you possibly want. Okay, let's move on to another example. So here, I'm going to assume that my data comes from a uniform distribution between 0 and theta. And theta is going to be some positive number. Okay, so theta is the upper bound of our distribution. And I don't know theta. Now, things to check. This is not an exponential family. Why? This means we could run into some trouble. If you look at the marginal distribution of any of my x sub n's, so 1 over theta for x between 0 and theta. And so here we notice that the support of my random variable depends on theta. And so some of the conversation about the previous one about paying attention to those indicator functions is going to matter. So let's look at how to tackle this problem. We can start off in a similar way. So first let's write the likelihood function, L of theta. And it is the product of my marginal distribution. Whoops, of my marginals, right? Which all have the form 1 over theta, indicator that xn is between 0 and theta. Now, the first thing I want to do is I'm going to break this thing up. This is really saying xn is bigger than 0 and xn is less than theta. And I know how to write that with indicators. I can say xn is bigger than 0 and multiply xn is less than theta. Right? Because that product is only going to be 1 if both are true. So when I push through this pi, this product here, of course I'll get theta to the negative n, or 1 over theta to the n, and then we're going to get these products of these indicator functions. The first one is the product of that the x sub n's are bigger than 0. And the second one is the product that the x sub n's are less than theta. Now, like the previous problem, we can read the product of indicators as and. So whenever you see the product of indicators, you read it as and. So the first one says x1 is bigger than 0, and x2 is bigger than 0, and x3 is bigger than 0, etc., 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 as we saw last time. So this is the indicator that all of them are bigger than 0, which we said last time is the same thing as the indicator that the minimum is bigger than 0. The min is bigger than 0, they're certainly all bigger than 0. If they're all bigger than 0, the min is bigger than 0. Cool. The second product we can play a similar game with. This is saying that x1 is less than theta, and x2 is less than theta, and x3 is less than theta, and etc. Right? And conversely, if we're looking at a less than, we could say that this product is the indicator that they are all less than theta. If they're all less than theta, the max is less than theta. And if the max is less than theta, they're all less than theta. So an equivalent way of writing this would be that the indicator that the maximum is less than theta. So this now nicely summarizes these complicated products of indicator functions into nicer statistics we are at least somewhat more familiar with. Minimum, maximum, we know those. So just to summarize, our likelihood function is theta to the negative n, indicator x1 is bigger than 0, times the indicator that the maximum is less than theta. Okay. So typically in the past, we have looked at the log likelihood function. We've done that because it's basically an exponential family, and that had some nice properties. In this case, that's not going to be as nice of a way to look at things. And the reason is it's not an exponential family, and this parameter, the support depended on the parameter. And so we get the parameter showing up in this indicator function. in a kind of weird way. Notice that more fundamentally, the L of theta isn't differentiable. That's not how you spell that. Differentiable with respect to theta. Why do I say that? Because as I change theta, if theta is smaller than the minimum, this thing is 1, and if it's just slightly bigger than, sorry, it's smaller than maximum, let's back up. Let's think about this, right? Okay. If theta is bigger than the maximum, the whole indicator is 1. If theta is less than the maximum, the whole indicator is 0. So you go from 1 to 0 as theta crosses through the maximum. And so this is the step function. It's a jump discontinuity where it will suddenly jump. And so it's not differentiable with respect to theta. And the reason it's not differentiable with respect to theta is because theta shows up in this indicator function. You're basically going to get this point, if I draw a little picture here, at xn, where we're going to jump. You're going to have something, and then you're going to jump to something else. Something like that. Not differentiable there. So you can't use the derivative in this case. Not going to work. The reason we didn't run into this in the previous problem is because the support didn't depend on the unknown parameter. And so you didn't have these problems where it potentially is not differentiable at various points. Okay, what do? Let's draw a picture of the likelihood function. So let's draw L of theta versus theta. And we already saw that this x sub n, this maximum, is an important point. So let's put that in, right? So this is my sample maximum, right? The world we're living in is we're imagining we've actually collected some data. And it has some values, 1, 3, 7, 4, 8, right? Some hard numbers, actually some numbers, right? You could calculate the maximum of those numbers. It appears somewhere, right? So this, in this case, this is not really, maybe I should write it with a lowercase x, right? This is kind of thought of as the sample maximum, but it's just some real number, right? And so we have our theta axis, and the x sub n appears somewhere in this theta axis. And we can plot L of theta. Now, okay. If we look at this indicator function here, if theta is less than the maximum, so that means we're kind of in this left-hand portion here, that indicator is 0. Because this says it's the indicator that theta is bigger than the maximum, so if theta is less than the maximum, so if theta is in this kind of left-hand portion here, where it's less than our maximum value, the indicator is 0, and the whole likelihood function is 0. So if I draw L of theta, it's just 0 everywhere here. Okay. Now we said we had this jump, right? So when theta is bigger than the maximum, so when theta is somewhere over here, right, we're basically trying to draw at theta. It's some function, we're going to maximize it. And it's not differentiable, so maybe we can figure this out if we draw it. All right, you can imagine basically testing different values of theta. If my theta were to be over here, then theta is bigger than the maximum, this is satisfied. We're assuming this condition related to the minimum is satisfied. If my data truly came from a uniform distribution, all of it's going to be bigger than 0. So this is always going to be satisfied by any sample. In any case, it doesn't depend on theta. It doesn't really matter. And so both of these will be 1s. And we're just going to get theta to the negative n. Theta is a positive number. Theta to the negative n looks like 1 over theta to the n. So it's some function that looks like that. All right, so this is basically 1 over theta to the n, or theta to the negative n. So it's some function like that, right? And I guess we have to draw it kind of like this. Okay. So, what's the maximum value of my likelihood function? This blue line is the likelihood function. What's the maximum value? Well, it's just going to be this point here, right? We can see that this is the maximum value. So maximum value attained there, which corresponds to my jump here, which corresponds to my maximum. So if I were to plug my maximum into my likelihood function, I would get this point, and that would be the maximum likelihood estimator. What that says is theta hat is my maximum. That's the whole story. Basically, I've drawn the picture, and I mean, you could make other loftier arguments. This is a decreasing function, and so the maximum's attained at the boundary of that. And so my MLE is maximum. Now let's go back up to the original problem, right? Our theta is uniform between 0 and theta. Theta is the upper end of that interval in which my data can live, right? It lives somewhere in this interval 0 to theta. If I collected a bunch of data, maybe some data, maybe these are my data points, that's where they lie. They'll be somewhere between 0 and theta. And now forgot what theta was, so you can pretend like you only saw this data here. What would you estimate theta to be? Well, you certainly wouldn't estimate it to be anything less than the maximum value you obtained, right? We have attained that little blue X there. And so theta better be at least that, right? And so a reasonable estimate say, well, the maximum value that can be attained, that's theta, well, let's just say it's the maximum value I observed, because that's what I observed. It certainly can't be smaller than that, because I observed something at least that big, so theta has to be at least that large. We don't know exactly what it is, but that's a reasonable estimate. And that's exactly what the MLE is telling us. The MLE is that the maximum, the most likely value is the maximum. So that's a little more complicated of a problem. Maybe much more complicated problem. It's not differentiable. So that kind of trick, this seems very much like a trick, a little bit of a trick. Now you've seen it. When I have to be more careful when my support here depends on theta. Because when that support depends on theta, it's not going to be differentiable. You can't just do calculus. One thing to do is see, can you just draw a nice little picture like this, and can you pick out the values? And this, I would accept this. And normally I don't kind of accept pictures as proofs. I would accept this as an answer on an exam. Let's look at another kind of advanced problem that you could see. Here, let's assume that my data comes from a normal distribution. But we've always said that, you know, I'm finding the maximum allowable value of theta. So like in the previous problem, we didn't let theta be negative. We had said theta should be positive. And many times implicit in these problems, like with lambda, implicitly I'm saying lambda better be positive, right? But for example, I could give you a problem and say, let's assume that I have data from a normal distribution, but maybe I know my mean has to be positive. It's a bit of a contrived example, but you could imagine a situation where you have some prior information that tells you that this thing has to be positive, right? So normally, for a normal distribution, the mean theta could be anything. It could be a positive number, it could be a negative number, etc. And I could say, let's assume that it's positive. So this is giving me a condition on theta. And to find the MLE, maybe I should write this down, it has to satisfy the requirements of theta. So it has to satisfy whatever constraints I give it. This is basically, I'm changing the underlying probabilistic model. People implicitly would assume that theta has to be, has no kind of restriction on it, but I could say, yeah, it has to be positive. That my probabilistic model of whatever data or phenomena I'm modeling, theta should be positive. So this is going to be a bit more complicated. Let us write some things down. So first, let's write the likelihood function, right? Now notice that my parameter theta, the support of my exponents doesn't depend on theta. That doesn't change. All I'm doing, so it's different than the previous problem. All I'm doing is putting a constraint on theta. So the product of my likelihood is basically the joint, which is the product of the marginals. Marginally, everything's normal. Okay, so those are the marginals. And again, there is no restriction on the x of n's. They can be positive, they can be negative. All we're saying is that that the distribution from which they are drawn has to have a theta that is positive. Maybe we should say bigger than or equal to 0 just to be technically correct. Okay, let's simplify this thing. 2 pi to the negative n over 2. Not, as you might be familiar with, that's not really going to matter. It's just some constant. And then what do we get? Push that product through, turn it to a sum and an exponential. And that's what we get. Might even expand this out more, right? Because there's kind of a clever way we can expand that out, isn't there? Let's think about it. In any case, basically what's going to happen with this problem is, let's think about what we said. I don't want to go through all the little details of this thing, but basically we said that this thing is basically a quadratic. I mean, basically it is in theta, right? It's going to be some quadratic function. You could think about this by expanding it out, right? Each of these are going to expand out into a theta squared plus some xn theta plus xn squared, right? And you sum it up, you get some number of theta squared, some number of linear terms multiplied by theta, and so it's going to be some quadratic in theta. You can expand it out and collect all the thetas together, convince yourself it's true. It's a quadratic in theta, and it's a quadratic in theta where the leading coefficient is going to be negative. Maybe we can get rid of basically. We just say this is a quadratic in theta. So it's a quadratic in theta where the leading coefficient is going to be negative because we have that negative 1/2 out front. And so if we were just to plot this function here, we would get something like this. Well, in fact, we wouldn't get that. we take the log likelihood, let's just do it properly, we can just bring that thing down. Okay, right? This is actually exponential of a quadratic. Let's actually make it a quadratic, right? We can instead work with the log likelihood function. It doesn't really matter. If we work with the log, now this is actually a quadratic. And so it would look something like this, right? It's going to look like negative x squared, right? Something like negative x, except in this case it's theta, so it's something like negative theta squared, right? Plus some other crap, but it doesn't really matter. This is a plot of the log likelihood of theta against theta. Okay, so it's basically this quadratic. And this should be familiar from the last time when we solved this problem, where we had seen that, unrestricted, so we haven't built in our constraint yet, unrestricted, this was maximized at x bar, right? And that is how we showed that in our previous problem, if we have data that's normally distributed, the MLE for the mean is x bar, which is cool. But now we have this restriction on theta, which is that it's positive. We don't have a restriction on the x's. They can be positive, they can be negative. They just come, right? If I could draw, they come from a distribution where theta is positive. But if I could draw data from a normal 1-1 distribution and still get negative numbers, right? Even if the mean is 1, that's just on average, right? There still can be, I could make draws, and some of those can be negative. So, and there could be, with some probability, that x bar is negative. And so we have two situations here that we need to contend with. One, x bar could be bigger than 0, or 2, x bar could be less than 0, right? And we kind of need to contend with that because, so you notice I didn't say neither is equal. This is the nice thing about doing probability is the probability x bar is equal to 0 is actually 0. Who cares? So I can always be sloppy with this kind of crap, right? Okay, so we have these two situations, which basically corresponds to 1, the 0 point is there, so x bar is less than 0, or 2, the 0 point is there. Maybe I should do it in a different color. The 0 point could be there, which corresponds to my second case where x bar, they write those arrows wrong. Yeah, I totally did, didn't I? Yeah. That is where x bar is positive. And the second case, if the 0 were to the right of x bar, that would mean x bar was negative, right? So those are my two cases. Why does it matter? Because I'm putting this constraint on x bar. I'm putting this constraint here, and my MLE must satisfy this constraint. If you go back to our definition of the MLE, theta hat is the argmin of L of theta, where theta ranges over some set of possible thetas. I call it capital theta. So it is, by definition, the minimizing value of theta over whatever set I say it is. Normally we say it's all values of all real numbers for this kind of situation, but in this case I say it is positive values. And so the MLE is definitionally has to be maximized, satisfying that constraint. And so, two situations. In the case where x bar is positive, this is easy. Theta hat is going to be x bar as before. So this is, let's say, case 1, case 2. Okay? Why? If, in this case, if 0 is over here, my likelihood function, or the part I'm maximizing over, is this part of the curve, right? Let me draw a new picture so I don't totally sully this one, right? So let's just draw this out real quick. L of theta versus theta has this quadratic. that corresponds to x bar at the top, right? So in situation 1, if my 0 is over here, I'm maximizing over the part where theta is positive, which is that region. And so that corresponds to this part of my curve. I'm maximizing over that curve. Well, it turns out that the global maximum without constraint is the same thing as the maximum over that red part. It's that little part there. Cool. Situation 2, redraw my dividing line. L of theta is theta. Here's this quadratic here. And corresponding to that top there is x bar. Okay. In situation 2, x bar is negative. So my 0 point is over there. Again, we're maximizing according to constraint, which is that portion. This now does not include my global maximum, right? If I kind of go up to the corresponding point in the curve, and I shade it in red here, we're maximizing over that part of the curve now. Because I'm just basically only maximizing over the allowable part where theta satisfies my constraint. So indeed, the maximum over this red portion, since the red portion no longer includes that global maximum at x bar, the maximum is going to be whatever the starting point is here, which corresponds to 0. And for this reason, theta hat, in my second case, is 0. Which is kind of unsatisfying, but it does make some sense. And so at the end of the day, so altogether, you could write this as theta hat has two cases. It's 0 if x bar is less than 0, or if x bar is positive. This will come up much later in the course when we talk about hypothesis testing. Okay, so this seems esoteric. I'm not going to hammer it now. I'm going to do this one example. This will come up a lot when we talk about hypothesis testing, because we're going to play similar games with the likelihood function, and we're going to compare. What if I want to test hypothesis? It's positive. Well, I need to maximize over the positive part. So this kind of thing will come up. So it's not totally esoteric. It will come up a lot in hypothesis testing. So it's good to kind of get some practice with it now. But altogether, this is my MLE. And that makes sense, right? So my data came originally from this normal distribution. And if I assume the data comes from some normal distribution with some mean theta, and this mean theta has to be a positive number, saying, the good Lord has told me that theta is positive, okay? So if I observe some data, I can calculate the mean. If that mean is positive, this is my second case here, I'm going to say, good estimate of theta is that mean. The data is a good estimate of the mean, of the population mean, and the sample mean is positive, the population mean, it has to be positive, everything's good. If instead I collect some data and they get a negative number for x bar, I know that the population mean can't be negative, because if I'm told from on high, it cannot be negative. So I cannot say the population mean is just x bar, because that would give me a negative answer. And that would not be a maximum likelihood estimator, because it doesn't satisfy my constraint. Instead, all I can say is that the population, or the sample mean is negative. And it turns out if the sample mean is negative, the most likely value, and it makes some sense, is that the sample mean is that the population mean is 0. And so my theta hat estimate, theta hat for the population mean would be 0. Because it's not going to be more likely, if my x bar is negative, it's not going to be more likely that the data came from some distribution with a really positive theta. It's going to be the most likely, the maximum likelihood estimator is when theta is if the population mean were 0. Okay. So it's a bit of a more complicated example. It will come back to bite us, not for the, probably for until we get to hypothesis testing near the end of the course. So For now, we're going to focus on the kind of simpler ones. Something like this uniform one is definitely fair game. Any of the ones where we just have some exponential family, we're taking a derivative, totally fair game. This will come back to bite us with hypothesis testing. Okay. Let's continue on doing some more interesting examples, right? I'm doing not just only exponential families because those are all just, okay, here, you take a derivative, blah, blah, blah. Kind of boring, right? And I want to leave some for you to do as homework. So I'm doing kind of the more advanced examples today. And the next example, this is a real fun one, is if I have some data, again, from a normal distribution, but my normal distribution has two unknown parameters. We have our mean, which can be any real number, and we have our variance parameter, which better be positive. So we don't really harp on multi-parameter families a lot. The only one we really spend a long time talking about is the normal, because it's relatively straightforward. But you could extend many of the things we do in this course to multi-parameter families. And for instance, we can just extend MLEs to multiple unknown parameters. And in this case, our likelihood is just going to be a two-variable function instead of a one-variable function. So what we'll get is a likelihood instead of just of one parameter mu, it'll be a likelihood of some mu and some sigma squared. And so to minimize this, we basically have instead of Calc 1 problem, we have a Calc 3 problem. So we can write out the likelihood, which is the product of the marginals. Each of these is marginally normal. Now we have this sigma squared parameter. So things get a little more complicated. But that is our PDF for a normal, which we'll commit to memory by the end of this course. You don't actually need to memorize it, but it's if you spend enough time doing these problems, you're just going to be forced to memorize it against your will. So we can simplify this. I like to simplify this as negative 2 pi to the n over 2. Let's just check that I did that correctly here. Yep, negative n. I tend to leave off the 2 there, right? Let's just, okay, so this is all exponential. Okay. I tend to forget that 2. Okay. And the reason I didn't include the sigma is because this stuff doesn't depend on either mu or sigma, and so it's going to go away when we take a derivative. Okay. But then we get a sigma. I'm going to write it this way: sigma squared to the again negative n over 2. And you might be tempted to cancel out the 1/2 with the 2 there. Do not do that. That we'll talk about why. We want to estimate an MLE of sigma squared. We don't want an MLE of sigma. And I guess it doesn't matter too much. Since you could write then by a transformation property, we'd be okay. But we don't want to have some sigmas and some sigma squares in other places. That gets complicated. We can combine these this exponential function, pull that common constant out, and that's what we'll get. And we're going to work, instead of with the likelihood function, we're going to work with the log likelihood function, which is again just a 2-variable function in this case. So we take the log of all this minus n over 2. And again, you'd be tempted to bring that square out, but just leave it for now. And we forgot our negative here. But our log nicely undoes that whole thing. So this is our log likelihood function. What do we do now? Step 2 normally would be we take a derivative set to equal to 0, and we solve. That's exactly what we're going to do. But now we have a two-variable function, so we have a gradient, or equivalently, partial derivatives. So we need to set both of them equal to 0. All right, so we need to do dl d mu, set that equal to 0, and dl d sigma squared, and set that equal to 0. So here is why we need to be careful about not getting rid of these squares, because we want to take a derivative with respect to sigma squared. Okay, so the first one is dl d mu. This first term disappears. Let's actually change our color just for the sake of it. First term doesn't depend on mu. Second term doesn't depend on mu. Goes away. This constant, negative 1 of 2 sigma squared, doesn't depend on mu, so it comes out as a constant. Okay? We can push a derivative through that sum, and we do a chain rule. This is 2xn minus mu. Derivative to the inner gives us a negative 1, right? Because this derivative of xn minus mu is just negative 1. Cool. And let's simplify this. That negative 1 cancels to the 1 out front. And that 2 cancels with that 2 indeed. So that's what we're left with. And we're left with that. We want to set that equal to 0. And in fact, we could even write this, we can push that sum through. And that would be the sum of the xn's minus n times mu. All right? Because I pushed that sum through. And we have the sum of mu n times. I can multiply by sigma squared on both sides. That doesn't change anything. So the sigma squared actually goes away. And what we get is that the sum of the xn's is equal to n mu, or mu is x bar. So we say mu hat, MLE, is x bar. Nicely, sigma squared disappeared. Didn't have to deal with it. This could be complicated. You could, in this kind of two-parameter setting, you could end up in that situation where you have a linear algebra problem where you have a system of equations you have to solve for one in terms of the other, and it could be even beyond linear algebra. It could be a non-linear system of equations, right? So it could be a disaster. Nicely though, sigma squared just poof, gone, and so we get mu hat MLE. So we know that the MLE for mu is x bar, which is nice and concerning because that's what it should be, right? We estimate the mean of a normal distribution. We estimate it with mu bar. We all know this. So again, more evidence. This is reasonable. It's reasonable not only when we don't know sigma squared, but it's reasonable when we know sigma squared. There's no particular reason they had to be the same, yet it is. The second thing we need to do is we look at dl d sigma squared. Now, I'm going to call tau, I'm just going to rename sigma squared tau. So, because I don't like writing this, that makes me nervous because I get confused. The first derivative, the second derivative, no, it's the first derivative with respect to, let's call it tau, okay? So we could just, everywhere we see a sigma, we could replace it with a tau. Sorry, sigma squared, we're going to replace it with a tau. Because it's weird taking derivatives with respect to squares of variables. So just rename the square to a single thing, okay? So derivative with respect to tau, so it's negative, the first term disappears, it's negative n over 2 times log of tau. Derivative of log of tau would be 1 over tau. So this is negative n over 2 tau. And we have some other junk that doesn't depend on sigma squared or depend on tau, but we have a 1 over tau. Derivative of that is negative 1 over tau squared. We already have a negative. Negative gives us a plus. And we have a 2 over tau squared. And then we have our xn minus mu squared. Now, our whole goal is to set this thing equal to 0, right? We basically have to solve the two equations, the system of two equations, right? Turns out the one involving mu didn't involve sigma squared at all, so it was easy. And this one does involve mu. However, because we're basically solving a system of two equations, we already know from the first equation what mu is. Mu is x bar, so you can basically replace that anywhere we see mu with mu hat, because we know that in order to solve the two system equations, right, you isolate one and then you plug it into the other, which is effectively what we're doing here. So we replace that mu hat or x bar equivalently. Doesn't really matter. And now we just need to solve for tau in this case. So let's multiply everything by 2 tau over n. Sure. So basically the reciprocal of this. Let's say, so this would be -1 multiplied by 2 tau over n, plus multiplied by 2 tau over n, I'll get 1 over tau, let's say this way, 1 over tau times 1 over n. Mu hat we call x bar. That seems correct. And now we just solve for tau. I move the 1 over, I multiply by tau. Tau, which is really sigma squared, we're just renaming it to keep ourselves from being confused, has the following form. And we can put hats on it, we can call it the MLE. So sigma hat squared, MLE, has the following form. 1 over n, sum of, over the ends of xm minus x bar squared. This looks really familiar. It's not quite what you think it is, though. This looks familiar. So backing up, we basically solved the problem at this point, right? This is the formula for mu hat, and this is the formula for sigma squared hat. So we have our MLE estimates for the now 2 unknown parameters here. This looks familiar. It's almost our s squared, right? S squared had a 1 over n minus 1, right? Right? And so it's like s squared, but instead of n over n minus 1, it has a 1 over n. So the MLE for sigma squared is not the same thing as s squared. We knew that s squared was unbiased for sigma squared. That's the expected value of s squared with sigma squared, which tells you that the expected value of sigma hat squared, the MLE, is not sigma squared. So in fact, it is not unbiased. Nonetheless, it's a totally reasonable estimator. MLEs are pretty much always very reasonable estimators. And so when people make a huge deal out of, oh, using 1 over n minus 1 versus 1 over n, kind of like, unless you really have a strong reason for preferring one or the other, sigma squared MLE is actually a kind of reasonable thing to look at, because or using 1 over n is very reasonable to do. So I don't tend to worry too much about it, because it's the MLE anyways, right? Which is, it's a reasonable estimator. For large n, it won't matter. And we'll talk about maybe next time smaller n. And maybe there's something better than either of those. Maybe there's a third option. So that's cute. Which basically, it basically says you couldn't do this for 2 parameters at a time. Probably not going to ask you to do that on an exam. You could see it on homework or on the suggested problems. But for the normal, it's a nice little, the 2 parameter normal is easy enough to do, and the MLE is x bar and this 1 over n version of the sample variance. Okay, let's do one more example, and then we'll pretty much be finished up with MLEs. At least the main part about MLEs for now. They're a super important topic in statistics. So MLEs are a huge deal because if you believe that the likelihood function encodes all the, that is the joint distribution encodes all the information about the unknown parameter, then the MLEs have a ton of nice properties, generally speaking. And we'll explore some of them in this class starting next time. But our last example is we're going to assume another kind of two-parameter example that the data come from another distribution. It's called the Laplace distribution. Maybe I can actually just write that out. It's called Laplace. There are multiple ways of parameterizing it. It's typically parameterized in terms of two parameters, mu and sigma. And that's not a typo. That is not sigma squared. It's mu and sigma. And the Laplace distribution has the following form. 1 over 2 sigma exponential of negative 1 over sigma x minus mu. So it looks a lot like the normal distribution, hence the two similar parameter names. But instead of the squared in my exponential, that would normally be x minus mu squared, it's the absolute value. And so I kind of answered this question about why don't we use this? And you could in some cases. In this case, the PDF has a graph that looks something like that. So it's symmetric around this value mu. And indeed, sigma squared will tell you something about, sigma will tell you something about the spread of the data. And mu tells me something about the peak. But it looks kind of like a tent. Instead of this kind of smoothish, it's going to have a actually a it's going to be not differentiable at that point there, which could cause some issues in finding an MLE. But it's again a two-parameter family, and so you can ask for the MLE. And in general, two-parameter families could be really complicated, but this is pretty nice. So we can ask for the MLE, and step 1, finding our MLE, is we write the likelihood function as two parameters, mu and sigma, and the likelihood is a product of the marginals. Each of these of our data points has this Laplace distribution, so 1 over 2 sigma exponential of 1 over sigma absolute value of xn minus mu. Done. What can we do? We can simplify this a little bit. Do the negative n, sigma to the negative n, exponential, negative 1 over sigma. Now we get, instead of the sum of the squares, we get the sum of the absolute values. And the second step typically is you would look at dl d mu, set that equal to 0, and dl d sigma, set that equal to 0. Now as a function of sigma, we're good because this thing is differentiable as a function of sigma. This is not differentiable with respect to mu. So that causes some issues. But we can at least get the sigma. dl d sigma is, if I were to fix my mu, this would be negative, well, let's look at the log likelihood. The log likelihood is negative n log 2 minus n log sigma minus 1 over sigma times the sum of the absolute values of xn minus mu. Let's look at dl d sigma. First term doesn't bend sigma, the second one becomes negative n over sigma, and then this becomes plus 1 over sigma squared times that. And So if we were to set this thing equal to 0, what we would find is that, so I could basically move some of these terms over. I'll let you do the algebra. You would find that, not sigma squared, but our parameter sigma hat is going to be 1 over n times the sum xn minus mu hat. Assuming I could figure out what mu hat is, in terms of mu hat, that would be sigma hat. Which is kind of cute, right? So this is very much like a normal distribution, but instead of having squares, we have absolute values. So that's real nice. Instead of sigma squared, we have sigma. And so assuming I can find what mu hat is, then I would be able to, the algebra just tells me that would be my sigma hat, which seems nice and reasonable. So mu hat, how do we get that, right? The problem is that this thing ain't differentiable with respect to mu because we have a mu in an absolute value. Nonetheless, if we look at this thing, it's, some constant, whatever, it doesn't depend on mu, times the exponential of, what is it? It's negative 1 over sigma it's that thing, right? And so basically, this is like, this is kind of like the exponential of negative a, right? So if we look at it, and so a has to be positive, right? This whole thing, obviously, is the sum of some absolute values, so that whole thing's positive. And so this would look like, what would it look like? It would look like the exponential function would be that. And so it looked like this. This is basically e to the negative a. It looks like that. And it's bounded below at 0, and kind of it would go like that. And so I guess it intersects, doesn't it? It doesn't, at 0 to 1, right? So this crosses at 1, right? Okay. So in order to maximize this, what we'd want to do, so to maximize, we'd make a as small as possible, right? If we wanted to maximize e to the negative a, we just choose basically as small as possible. And that's going to be true here. And we may not be able to make it 0 exactly, but you could just make it as small as possible, because even if you could only make it that small, you always want to be going this way towards that 0, right? And so we want to make sigma is obviously just number, and we just want to make that sum as small as possible. So the idea is to make this thing as small as possible. And so we're going to choose mu to make this thing as small as possible. What value of what value of mu makes this sum of the absolute values as small as possible? So there's a fact, and I'm going to write down 2 facts. The first fact is that if I were to replace this with a square, like in a normal distribution, this is minimized if mu is equal to x bar. That's actually something we've shown a million times. Anytime you do an MLE for a normal, you've shown that fact, basically. I haven't thought of it in that way, but you do. And you can prove this with calc 1. Okay. Take a derivative with respect to mu, set the derivative equals 0. Turns out the minimizer is x bar. So that's fact 1. Fact 2, the one we're more interested in, if I replace those squares with absolute value bars, this is minimized if mu is equal to what? Is equal to the median of the x's. My sample, for example. So that's really cute. If I minimize the sum of the squares, I get the mean. If I minimize the sum of the absolute values, I get the median. And that is indeed true. So what you would be able to say, if you believe this fact, and we can show it, we can make an argument that mu hat will be the median. So the MLE for mu is the median, and then the MLE for sigma is we take whatever xn, subtract off the medians, take the absolute values, and take the mean of those. So this whole thing is like a more robust version of a normal distribution in some ways. We replace squares with absolute values. Okay, so proof of the second fact. Why? This is a fun kind of pictorial proof. It's not really analytical. I'm going to assume I have some data points. Here's my x's. They're going to lie something like this. And let's assume we have 5 of them. And so if I have these 5 points, this is my median. And I want to minimize the sum of the distance of xn to mu. So this is going to be, kind of think of this as my mu axis. And what I could imagine doing is I could imagine starting over here somewhere. That's a candidate mu. And I could say, if I put mu there at that red dot, does that minimize the sum of my squares? Sorry, does that minimize the sum of my absolute values? The sum of the absolute values is basically the total distance of the xn's to my putative mu, right? Each of these is the absolute value is the distance between xn and each of the xn's and mu, and so I sum them up. It's the total distance. So if I put my red dot there, what's my total distance? What is my sum of my absolute values? It's distance of the red dot to this first x, red dot to the second one, red dot to the third one, red dot to the fourth one, right? So it's the sum of all of those. The question is, does that minimize it? If it does minimize it, I shouldn't be able to move anywhere and find a smaller total distance. However, if I were to move my red dot to over here, I've decreased the distance of the red dot to all of these 5 x's, because not only is this second red dot, so let's call this 1 and this 2, this red dot 2 closer to this first one, is closer to the second one, and the third and the fourth and the fifth, right? And so I could certainly keep moving like this to a position, say 3, and that has a smaller total distance of this red dot to all of my data points. And I could play this game, I could even jump through this first x. Because if I move from somewhere on this left side to somewhere on the right side, I will maybe increase the distance of the red dot to this first x by putting it over here. So I've increased the distance to one of the x's, but I've decreased it to 4 other x's. So my total distance goes down because I've increased it for 1 and decreased it for 4. And I could keep moving this way. I've increased it, if I move over here, the distance of my red dot to my first x, but I've decreased it to 1, 2, 3, 4 other x's. So my total distance decreases. And I could keep playing this game, jumping along here. At each point here, now I've increased the distance to 2 of my x's, but decreased it to 3. So on net, I've decreased the distance. And I can keep playing this game until I jump and hit my median. At which point, when I hit my median, if I were to move anywhere to the right now, I would increase the distance to more points than I decrease it to, definitionally, by the definition of the median. And so I would not be minimizing it. So basically, I jumped over and I found the point that minimizes it. Because if I moved either to the right or the left, I'll increase the distance to 3 points, and decrease it to only 2, and my total distance, that is the sum of the absolute values, would increase. And so if I want to minimize that sum of the absolute values, I should stick my mu hat right here at the median. That's a cute little pictorial proof. And that gets me my MLE of the median. Okay, so we're kind of out of time here. And that's our kind of second lecture on MLEs. And next time we'll start talking about evaluating all the different estimators that we've got.